turning. We don't even talk about a P and an R branch. They just keep going all the way. And they will only turn around if you throw in centrifugal distortion, which is not what we are discussing at this point in time. So if B equals B naught equals B1, there is no band here. So if B naught equals B, just about equal to B1, slightly different, then the bandit will start to appear. But where will it turn around? At a much larger value of J. But if B naught and B prime or B naught and B1 are very different, or significantly different, then the turnaround will occur at a much larger value, at a much smaller value of J. How do you rationalize by looking at the equation? All I am saying is the coefficient of J square term, which is the one responsible for the turnaround, is much larger when B naught and B1 are different. So if the J square term is a bit larger coefficient, then the bandwidth is quite pronounced. And that's the reason why it would turn around quite easily. So in this case, which one would turn around at a smaller value of J? The one that has a bigger difference between R and R prime. And therefore the B to H transition, which has got a much bigger difference between the two B values, is the one that will turn around at a lower value of J. The other one almost has the two B values nearly equal. Therefore they will just keep going. They won't turn around as quickly as the other transitions will. Okay. So that's basically, again, all I'm trying to do in this case, instead of asking you that equation, you take that equation which gives you the frequencies for the P and R branches, and let's ask you to apply that. If B values are very different, then the banded formation is quite pronounced and happens at much smaller values of J. So all I have done is asking you, by giving you two B values, I have just given you two potential curves. And I'm asking you to draw inference from the potential curves so that you can answer this question of where the turnaround actually happens. Any questions? Let's go to the third one. What states arise from? This is for the you have the P branch and you have the R branch. Now, if you remember the equation that we had, where we had, I think, is plus B0 plus B1 equals J, and then minus B1 equals J squared, things like that. Right? So, if this one was positive, then this would actually negate this value. Then it is a turnaround effect. But if this one is negative, then what happens? This becomes positive, and this only adding on to this, there is no turnaround. So this keep on going in one direction. Now this value is positive or negative, it's different for the P and the R branch. So if you fix this for a given transition, this is fixed. If this was positive, then with a negative sign it would turn around. But if this was positive, with a positive sign it would not turn around. Now P and R, they change in sign right here. That's the reason why you have one or the other turning around. Let's look at the third question, which is basically a term state question. And what we were looking at, we saw in the last exam, the second mid-set, how term states for atoms could be got. Right, and we looked at some simple ones. Then of course we went back and did for carbon, which was much more pronounced. So we had to go through a lot of number work before we got the states of carbon. And the reason why we had to do that was because in carbon we were looking at equivalent electrons, P2. And therefore you had to employ the Pauli exclusion principle, and you had to throw away some states which could not be acceptable for that given situation. Therefore we had to throw away some, out of 36 states, I think we threw away 21, kept 15, we Pauli allowed combinations, and then we came up with the term states for carbon, which was triplet P, singlet S, and singlet D. In the case of molecules, what do we do? Just like we use electronic configuration for atoms to get the term states for atoms, we use the electronic configuration for molecules, in the molecular orbitals, and then we come up with the term states for molecules. That's one way of doing it. There are other ways of doing it, which we haven't studied at this point in time. Maybe when you do an advanced course on molecular spectroscopy, you will learn those things. There are other ways to do that. But here we just looked at the electronic configuration in molecules, and we came up with the term states. Now, the case of molecules, how did we label states? Just like in atoms we had single S or triplet P, where what was S and P? They were the values of L, they were the orbital angular momentum. If L was 1, it was a P state, L was 0, it was an S state, and so on. And what are these numbers? They were the spin states, 2s plus 1 values. So this essentially fixed for us what the state of the molecule or the atom is. Of course, we have to give the J values. Triplet P would give me triplet P, 2, 1, and 0 as 3 possibilities. Single S would give me 0. So this is 0, spin is 0, there's nothing to really to add, and it would be 0. This would be 2, 1, and 0. And we also saw whether 2 is a ground state or 0 is a ground state, depends on whether the configuration came from a more than half moon situation or a less than half moon situation. In the case of molecules, what we do? We have very similar arguments, excepting that because the cylindrical, and we only did for diatomics, we didn't do for polyatomics. We did for diatomics. And for diatomic, there is this axis which acts as the symmetry axis, and we were looking at the projection of this angular momentum on this axis and labeling all our states based on that projection. So the equivalent of S was sigma, and what does sigma immediately mean? The orbital angular momentum projection on the nuclear axis was 0. The equivalent of P was pi, and what does pi tell me? That the projection on the axis was plus or minus 1, not plus 1, 0, minus 1. No, it's plus minus 1, that's it. If it is delta, what's the projection going to be? Plus minus 2. So you will see that plus pi has got a double degeneracy, meaning it's got a plus 1 possibility or minus 1 possibility. Delta has got a double degeneracy. What's that? Plus 2 or a minus 2. And so on. So these are basically situations. And as far as spin is concerned, you just give the same notation as before. I can have single sigma, single pi, triplet sigma, triplet pi, and so on. So in the labeling states by the values of L for the atom, we are now labeling states by terms of the projection of the orbital angular momentum on the internuclear axis, and that is given the symbol lambda. So what is L for atoms is actually lambda for the molecule. If lambda is 0, it's a sigma state. If lambda is 1, it has two components, plus minus 1, it will be a pi state. Lambda 2, a delta state, and so on. So if you had to figure out what the term state for a molecule is, you actually have to only calculate what the lambda value is for a given electron configuration. What we have done in the third problem is I have given you an electron configuration for a carbon species, C2, for diatomic. And you know what the configuration is? 1s, 1s will give me 1s sigma, 1s sigma star, 2s and 2s, 2s sigma, 2s sigma star, and then 2p pi, which comes from the x and y component of the p orbital, and this is 2p sigma, 2p pi star, 2p sigma star, right? But of course, this is valid for carbon and nitrogen. But then when you go to oxygen and later what happens? This moves around. The pi comes on top and sigma comes lower. In fact, that's what you would have thought in the first place. This is an inversion, really. So after nitrogen, you have a weird situation. After nitrogen, I think some sanity is restored. We get this back. Now, what did I say there? I said it is beryllium 2 in bracket, and then I've given some configuration. What does that mean? I'm simply saying that the first part of the electronic configuration is simply what you would have in beryllium. And this is something we use even in atoms. If I have to give you the atomic, the electronic configuration for iron or something, we don't write everything. We write the inert gas configuration up to one before that, maybe R0. We just say R0, and then we just give the rest of it. Meaning, up to there, it's something that you already know. So I said BE2, and then followed by 2p pi 3, and 2p sigma g 1. So this simply means, first fill up as if you are filling up a beryllium. How many electrons do you have in beryllium? Lithium is 3, beryllium is 4. So basically beryllium 2 would be 8 electrons. So fill it up, and 8 electrons would simply go here. This is the configuration of beryllium, and all I am saying is, in this case of carbon, take this as grounded beryllium. And then I say it's 2p pi u3 and 2p sigma g 1. I'll take simple carbon ground state. What would be the electronic configuration? Carbon needs 4 more electrons, right? C2 needs 4 more because beryllium has 8, carbon has 12. So 8, 9, 10 and 11, 12. This would have been the ground state for carbon. If this is the ground state, what would be the term state for carbon? Completely filled. Everything is filled. So if everything is filled, what's the state? Singlet sigma. Just like if everything is filled in atoms, it's singlet S. That's why I didn't give you this, because it's trivial. But then I wanted to make it a little bit more complicated. I said remove this guy and put it here. That's an excited state of carbon. And when you have an excited state of carbon, this is the electronic configuration that I was referring to. 2p pi u3 and 2p sigma 1. Sigma orbitals are always going to be of G symmetry. Because provided I am looking at a homonuclear diatomic. If it is heteronuclear diatomic, like let us say it's carbon and nitrogen, Cn, then there is no center of inversion, therefore there is no way you can classify states as GU. GUs don't even exist. But wherever I am looking at a homonuclear diatomic, then I have to label states by GA. And what are sigma states? G states. And what are sigma star states? U states. G, U. What about pi states? Pi is U. And pi star is G. Sigma is again G. Is U. So that is basically the sigma, the UG notation for all these states. And assuming that we all are clear as to why a sigma state is G and why a pi state is U. Anybody has a question on that? But if you want me to go through that, I will do it because you need to understand this. You want me to do it? Yes. Let's take hydrogen. S orbital, S orbital. I bring them close to each other and they form a molecular orbital. Now when I get them close to each other, how many possible ways can I get them close to each other? There's a phase for the wave function, right? So I can have plus and a plus on the other one. If it's plus and plus, that means they're in phase, then what happens? You have a constructive build-up of the electron density between the two nuclei. And there's a constructive build-up of electron density between two nuclei. Electron density is sitting right here. Then what happens? The two nuclei are basically shielded from each other and they don't repel. So that's basically how your bonding basically happens. If I completely strip this region of all its electrons, then what will happen? The two positive charges are basically looking at each other and they would simply repel and go away. The only reason they are not doing that is simply because the electrons are basically concentrating themselves between the two nuclei. And that will happen if this is plus and this is plus in phase, and therefore you will find H and this H overlapping, and what would you get? If this happens, what's the symmetry of this? Does it have an inversion symmetry or not? Not the way I have drawn it, but then you would have an inversion symmetry. However, if this was plus and this was negative, then what would happen? When these two come, they will repel each other because they are basically destroying each other. So in the region between the two nuclei, there is no electron density built up. And what would you expect to see? You expect to see a minus here and a plus here, with hardly any electron density built up. And that is the reason why the state actually is an antibonding state. Because when this happens, the two nuclei will simply want to get away. There is no contribution to bonding in this situation. Plus and a minus. So what should be the symmetry of the state? A U symmetry. And that's the reason why antibonding orbitals have a U symmetry. What is the p orbital? The p p orbitals plus minus plus minus. The two p orbitals come along the z axis, and I'm talking about the pz orbital. What will this give rise to? Bonding or an anti-bonding situation? Bonding situation, because there is some subtle interference between these two loads. What would be the net picture? These two negatives would go here, positive, and therefore what is this structure going to be? Again, giving allowance to the beauty of my structure, it's G or G symmetry. G symmetry, because this will reflect on this, there is a center of inversion in this function. Therefore, again, there is a bonding orbital, and this was G symmetry. If I change the sign over here, then what happens? Again, there is no build-ups, because these two are of opposite sign, and therefore what is the symmetry of this going to be? U symmetry. So you will find that P sigma, Pz actually gives rise to two orbitals. One is P sigma and the other one is P sigma star. The P sigma has G symmetry, the P sigma star must have U symmetry. So in general, if I am looking at sigma orbitals, G, sigma star orbitals, U. This is my bond direction, and these orbitals are oriented orthogonal to that. Therefore, I am really talking about a pi orbital. Now, what will happen in this case? There will be constructive interference because they have the right orientation. And therefore, what would I get now?